is another example. We have a matrix, and we want to find all eigenvalues, eigenvectors, bases for the corresponding eigenspaces. So we apply standard procedure. Step 1, find eigenvalues. We write down the characteristic equation. We rewrite the determinant as the characteristic polynomial 5 minus lambda, 1 minus lambda. And we see that our characteristic polynomial has the following roots, 1 and 5. These are eigenvalues. For each of these eigenvalues, we find the corresponding eigenspace. Again, we apply the standard procedure. Lambda is equal to 1. Step 1, we write down the corresponding augmented matrix. We replace lambda by 1, and then we apply elementary row operations to come up with the reduced echelon form. We switch to the corresponding equation. We replace x1 by 0, factor out x2. Here's a complete description of all eigenvectors. Therefore, this is the corresponding eigenspace, and therefore 0, 1 is its basis. Similarly, for lambda is equal to 5, here is augmented matrix. We replace lambda by 5 and apply elementary row operations to come up with the reduced echelon form. We switch to the corresponding equation. We move 2x2 to the right because x1 is a basic variable, x2 is a free variable. And then we replace x1 by 2x2, factor out x2, and here's a complete description of all eigenvectors corresponding to lambda is equal to 5. This is the eigenspace, and here is its basis. Folks, any questions here?
Just to make sure, so that an eigenvector is if you choose a specific value for t.
Yeah, so here we have infinitely many eigenvectors corresponding to lambda is equal to 5. Now, if you assign a specific non-zero value for x2, you will come up with a particular example of an eigenvector corresponding to lambda is equal to 5. Was that a question?
Yes, thank you.
Other questions?
Why do we care about eigenvectors?
Exactly. It's a very good point. Why care about eigenvectors and eigenvalues? We will discuss applications in the second part. Other questions?
So as a general rule, you could say that the basis for H is just plugging in 1 for x2 in this case?
We can plug in any non-zero or real number in order to find basis.
Right, okay, thank you.
Sure. Next. Please take a look at this matrix. Very similar exercise. We write down characteristic equation. We rewrite this determinant as a characteristic polynomial. Eigenvalues are 1 and 5. And then we apply the standard procedure to find the corresponding eigenspaces. For lambda is equal to 1, step 1, write down the augmented matrix. Step 2, replace a lambda by 1 and apply elementary row operations to come up with the reduced echelon form. After that, we switch to the corresponding equation. We move 2/3 x2 to the right because x2 is a free variable and x1 is a basic variable. Then we replace x1 by this expression, and then either we can factor out x2, or here I decided to factor out 1/3 x2 in order to have only integers inside. These are eigenvectors. this is the eigenspace. Negative 2/3 is a basis. You may ask me a question, what happens if you factor just x2? Then inside we'll get negative 2/3 1, here negative 2/3 1, and here negative 2/3 1, which is an equivalent way to describe the eigenspace and a basis. Similarly, for lambda is equal to 5, augmented matrix, elementary row operations to obtain a reduced echelon form, we switch to the corresponding equation. We move 2x2 to the right because x2 is a free variable, because it corresponds to a non-pivot column. x1 is a basic variable because it corresponds to a pivot column. Then we replace x1 by negative 2x2. We factor out x2. Here are eigenvectors. Here is the eigenspace. And here is a basis. We're done with this exercise. One last time. Any questions?
If you would have the same number that you're replacing it 2 times, you just have one eigennumber or eigenbasis?
Excuse me, can you repeat once again your question?
Sorry, if you were replacing lambda by the same number, would you just have one vector then? If lambda 1 was equal to 2 and lambda 2 was also equal to 2?
What if both roots are equal? Is this your question?
Mm-hmm.
Very good question. We will discuss it in section 3.10, equal roots.
Okay.
Basically, partially, we will discuss it in this example. Please take a look. We have a 3 by 3 matrix. Therefore, the corresponding cubic polynomial will have 3 roots. But actually, if we do computations, it turns out that this polynomial of degree 3 has only 2 distinct roots. See what happens in this case. So for lambda is equal to 2, we write down the corresponding augmented matrix. We replace a lambda by 2, apply elementary row operations in order to come up with a reduced echelon form. Now, pivot column is number 1. Number 2 and number 3 are non-pivot columns. Therefore, once we switch to the corresponding equation, we move both terms to the right. And here is a complete description of all eigenvectors. Now, we split this matrix column and work is over here into 2 pieces, this plus this. Therefore, what we see in front of us is the eigenspace, and its basis consists of 2 vectors, vector number 1 and vector number 2. Any questions here?
I had a question about an earlier thing. Could you repeat
Yes, sure.
why you start by setting the determinant equal to 0?
Very good question. So are you talking in particular about this example?
Sure. I mean, in general,
So
yes.
the question is, why all of a sudden to find lambdas, we set up this equation, correct?
Yes.
It's because of this. Note that in order to find all non-trivial solutions of this equation, step 1, we replace t of x by ax, and then rewrite ax is equal to lambda x as this. Here is work. What we see in front of us here is a homogeneous system of linear equations. And this corollary that we discussed in section 3.7, this one. This corollary tells us that a homogeneous system of linear equations has a non-trivial solution if and only if determinant of A is equal to 0. In our case, our matrix is A minus lambda I. So if lambda is an eigenvalue, lambda satisfies the following equation. Determinant of A minus lambda I is equal to 0. Does this answer a question?
Yes, thank you.
Other questions?
So for the H vector spaces, are those are in correspondence to the lambda values or the eigenvalues?
Absolutely.
Okay.
Have several distinct eigenvalues. For each eigenvalue, we have the corresponding eigenspace.
Okay.
So for lambda is equal to 2, the eigenspace is two-dimensional. However, for eigenvalue number 2, which is 9, we apply the same procedure. We come up with a corresponding system of equations. We move the free variable to the right. We replace x1 by x3. We replace x2 by x3. We factor out x3. So for the second eigenvalue, which is equal to 9, the corresponding eigenspace is one-dimensional, and here is its basis. Okay, and now let me address the following question. Simple question, why care about eigenvalues and eigenvectors? First of all, let me start with theorem 12. Theorem 12 says that any k eigenvectors v1 and so on vk with distinct eigenvalues lambda 1 and so on lambda k are linearly independent. In simple words, we start with a square matrix A. We find all distinct eigenvalues. For each eigenvalue, we find the corresponding eigenspace. Then we pick an eigenvector from each of these eigenspaces. Theorem 12 says that these eigenvectors will be linearly independent. Any questions about theorem 12?
Wait, how do you define a distinct eigenvalue?
Distinct means not equal. Let us go back to this matrix. One can show that the corresponding characteristic polynomial has 3 roots: 2, 2, and 9. The first 2 roots are equal. So despite the fact that our cubic polynomial has 3 real roots, it has only 2 distinct roots. Does this answer your question?
Yes, it does. Thank you.
And now applications, guys. Let us go back to systems of differential equations. We already discussed how to solve such systems in section 3.1. For example, please take a look at this. We discussed several examples. Let us go over this example once again. In order to solve this system, either we solve equation number 1 for x2, which is done here, and then plug in into the second equation, or we solve equation number 2 for x1, and we do it over here, and then plug in into the first equation. It turns out that eigenvectors and eigenvalues allow us to solve these systems in a very different way. Here is the most important formula. X of t, a particular solution of our system, can be written as e to lambda t times v. where lambda is an eigenvalue and V is an eigenvector from the corresponding eigenspace. Conclusion, if you combine what is written here with theorem 12, here is how we can come up with a general solution of our system. If we are able to find n linearly independent eigenvectors, then in order to come up with n linearly independent particular solutions, we multiply these eigenvectors by e to lambda t, where lambda is a corresponding eigenvalue. Done? Think about questions.
I'm guessing explaining how we got that equation is too complicated.
Well, you can take a look at proof. Not really complicated. So x of t is e to lambda tv. We take the derivative of this, done. And then we plug in this into the left-hand side and the right-hand side. X dot means derivative, as we discussed. If we plug in this into the left-hand side becomes this. We plug in this into the right-hand side becomes a times e to lambda tv, which is exactly what is written here. And then, since e to lambda t is a constant can be factored out. And now, let us put pieces together. This is left-hand side, this is right-hand side. Left-hand side should be equal to right-hand side. It's exactly what is written here. But then note that e to lambda t is a common term. It can be cancelled out. Once we cancel e to lambda t out, we get AV is equal to lambda v, which means a lambda is an eigenvalue, v is an eigenvector. Does this answer your question?
Yes, it does. Thank you.
I think
Other
something
questions?
was
Yeah.
missing in the proof.
What is missing?
On the left-hand side, where the derivative should be, the lambda is missing for a e to the power of lambda tv.
Lambda is here. So on the left-hand side, we take derivative of e to lambda tv. And then by chain rule, e to lambda t prime is lambda e to lambda t.
When you plug into the x dot is equal to x, ax,
Yes, yes.
if you look on the next step above, yes.
This is only the right-hand side.
Oh, okay, never
Left-hand
mind.
side, this is right-hand side. Our left-hand side should be equal to right-hand side. Here's what we get.
Okay, yeah, thank you.
Now, let us talk about applications. We already solved this system in section 3.1. This solution is solution number 1. But now, solution number 2, eigenvectors and eigenvalues. So, step 1, identify A. Looking at this system, one can easily conclude that A is 7, 4, -3, -1. Next, we find the characteristic polynomial, his work. We subtract lambda from the main diagonal. We expand this determinant, expand all parentheses, collect like terms. Here is the polynomial. And it is easy to find its roots. Lambda is 1, lambda is 5. Then, for lambda is equal to 1, we apply the standard procedure in order to find all eigenvectors. Therefore, a particular solution will be e to lambda t. Remember, lambda is equal to 1, so here we have just e to t times an eigenvector. For example, -2, 3. We don't have to put x2, 1/3, x2, because all we need is to put here an eigenvector. There is no need to put here all eigenvectors, just one of them. And the reason for that is the following. Later, we will multiply this particular solution by C1 anyways. So here, e to lambda t times some eigenvector. For example, -2, 3. We apply same procedure for lambda is equal to 5. So once again, augmented matrix, we replace a lambda by 5. We apply elementary row operations to come up with the reduced echelon form. We switch to the corresponding equation. We move 2x2 to the right because x2 is a free variable. And then replace x1 by -2x2, factor out x2, and here are all eigenvectors. Particular solution number 2 is e2 lambda t times v. Lastly, in order to find the general solution, we multiply particular solution number 1, which is over here by C1, plus particular solution number 2 times C2. Done. Questions here?
Is it possible to have imaginary solutions for lambda, and what would happen then?
Absolutely. Imaginary solutions will be discussed in the next section, which is called complex roots.
Okay, thank you.
Questions? Last example. Here we have a 3x3 system. Note that in section 3.1, we discussed only 2x2 systems. Of course, question is it possible to use the substitution method in case of 3x3 systems? The answer is yes, but then in this case, the sequence of operations will be even more confusing. Note that if you solve a system using substitution method, solution is not short at all. However, if we apply eigenvectors, eigenvalues method, the structure of the solution is fundamentally same. Step 1, we find characteristic polynomial. By the way, since our matrix is 3x3, it takes quite some time to find characteristic polynomial. But here all steps are shown. Step 2, again, pretty complicated procedure. Since we have a polynomial of degree 3, big question is how we find its roots. Again, what is shown here? We factor this polynomial. So the eigenvalues are lambda 1 is equal to 1, lambda 2 is equal to 3, lambda 3 is equal to -2. And then for each eigenvalue, we find the corresponding eigenspace. For lambda is equal to 1, augmented matrix, we replace a lambda by 1 and apply elementary row operations to come up with a reduced echelon form. We switch to the corresponding system. We move the free variable to the right. And here is a complete description of all eigenvectors. Once again, important, when we jump from here to here, we leave the free variable without change. We replace only basic variables by the corresponding expressions. So here are eigenvectors. Therefore, here is a particular solution number 1. Similarly, for lambda is equal to 3, we apply similar procedure. We come up with a reduced echelon form. Now it takes quite some time to find the reduced echelon form. We switch to the corresponding system, move x3 terms to the right, and here is a complete description of all eigenvectors corresponding to lambda is equal to 3. Therefore, this is particular solution number 2. Lastly, for lambda is equal to -2, we apply again same procedure, and here are all eigenvectors. Therefore, this is particular solution number 3. Lastly, the general solution of our system is C1 times particular solution number 1 plus C2 times particular solution number 2 plus C3 times particular solution number 3. We are completely done. Any questions?
So, are you saying that doing this method with eigenvectors is simpler than substitution?
No, I've never said that.
Okay.
So for 2x2 systems, I would say the method of substitution is probably easier. For 3x3 and bigger, easier to apply eigenvector, eigenvalue method.
Okay, thanks.
Other questions?
So sometimes when we find an eigenspace
Mhm.
from like a particular lambda, sometimes there's two eigenvectors.
So we start with an n by n matrix. We find eigenvalues. If the number of eigenvalues is n, we are fine. But if the number of eigenvalues is lesser than n, we might run into problems, because the sum of dimensions of corresponding eigenspaces is lesser than n. Here's what I mean by that. Please take a look at this problem. This one. Know that this is a 3x3 matrix. However, this 3x3 matrix has only two distinct eigenvalues. Fortunately for us, the eigenspace corresponding to lambda is equal to 2 is two-dimensional. Therefore, we are able to create two linearly independent solutions if lambda is equal to 2, and then a lambda is equal to 9 gives us independent solution number 3, and we are good. We have 3 linearly independent particular solutions of our system. However, sometimes we have, say, a 3x3 system, only 2 distinct eigenvalues, and for each eigenvalue, the dimension of the corresponding eigenspace is only 1. This case will be discussed in section 3.10. Was that a question?
Yes. Thank you.
Other questions?
Can we go back to the -2, 3 eigenvector example?
I think your question is about this example, right?
Yeah, so I see that we factored out the 1/3 and the x2. So can you explain why we don't need to worry about the 1/3?
Very good question. This is because x2 is any non-zero number. So let us compare two expressions. 1/3 x2 times this. And then expression number 2, just x2 times this. Both expressions give us same set of eigenvectors because x2 is an arbitrary number. Remember, going back to differential equations, if we have, say, c1 times e to t or 2c1 times e to t, this is the same set of functions because c is any constant. Same is here. Since x2 is any constant, it does not make any difference. We have x2 in front of this vector or 1/3 x2 in front of this vector. Both expressions, 1/3 x2 and just x2, can create the whole set of real numbers. Does this make sense?
Yes, it does. Thank you.
Other questions?
Could we go to the two-dimensional, the one with the same roots, however, was still
Yes.
two-dimensional? I was wondering, So let's say that the original matrix we had was a differential equation. And I was just wondering, so let's say we got the eigenvalue equal to 2 here,
Yes.
like we did. So
Yes.
would it then become like e to the power of 2t and then
Yes.
t e to the power of 2t?
Very good question. Please take a look at this formula. The formula is e to lambda t times v. So
Yes.
going back to our example, in order to come up with 3 linearly independent solutions, we do the following. Particular solution number 1 will be e to 2t times this vector. Particular solution number 2 will be again e to 2t times the second vector. Lastly, particular solution number 3 will be e to 9t times this vector. Done.
I see. Thank you.